Sure, I just started recording. So whenever you're ready.
Give me 1 minute, sorry. Okay. Yeah, hi everyone. Welcome to the 8th lecture of the 2025 Invited Seminar Series organized by IEEE Computer Society San Diego chapter. And it's our pleasure to have Dr. Ali Siahkoohi from UCF. This event is co-hosted by the Computer Society chapters of Pikes Peak section, Buenaventura section, Hawaii section, and Dallas section. And as always, our media partner is Open Research Institute. With that, I'll hand it over to Dr. Piraj Khurram Shahi, our Computer Society Chapter's Vice Chair, to introduce today's guest speaker.
Sure. Thank you, Paul. Hello, everyone, and thanks for joining. Today, we are pleased to have Dr. Ali Siahkoohi, who is an incoming tenure-track assistant professor in University of Central Florida's Computer Science Department. Currently he's a Simons postdoctoral fellow in the Department of Computational Applied Mathematics and Operations Research at the Rice University, jointly hosted by Dr. Martin Dehoop and Richard Baraniuk. He received his PhD in computational science and engineering from Georgia Institute of Technology in 2022. His research focuses on designing scalable methods for quantifying uncertainty in AI models with a broader goal of enhancing AI reliability. So with that introduction, Dr. Siahkoohi, the floor is yours.
All right, thanks, Biraj, and thanks to Paul for the invites, and the introduction was pretty neat. Thank you. So you said it right. So I work on uncertainty quantification in computational science and engineering, and typically that involves sampling from distributions, very dimensional distributions. So one way of doing that scalably is via approximating these distributions using neural networks, and generative models offer a natural framework to do that. So most of my work is on generative models, and I'm super excited to talk to you a little bit about one aspect of my work. And yeah, so it's going to be about a particular phenomenon that is happening, whether we like it or not, in the context of the way these large-scale generative AI models are being trained in industry. So essentially what happens is these AI companies scrape the internet to get data, and then they train their large-scale generative models on the data set, right? So we might unintentionally get data from the internet that is generated from previous generations of generative models, right? So we all use generative AI, and we might paste some of its outputs to the internet, and once scraping happens again, the synthetic data is going to end up in the training data sets. And that's what I mean by self-consuming generative models, right? So I'll dive deeper a bit more. And this work is going to be all about, first, in this talk, I'm going to talk about, first, what is a self-consuming generative models in more detail, and what happens if we keep on doing that. And finally, I'll talk about an approach that we could perhaps mitigate some of the biases that happens when you fall into this self-consumed loop, right? And this work was sort of featured in New York Times as well, and it got a lot of attention when we put it online two years ago. And I'm very happy to hear if anybody has any comments or arguments, because there are two different camps now. Some people prefer to use synthetic data, and they claim they get gains from it, but here we're going to warn people against it. So with that, let me get into it. Okay, first slide. So this work is joined by many people at Rice University. This was done when I was a postdoc there. I still am for 2 months. And yeah, as I said, most of us use generative AI models, whether text-based or image-based. And what happens is when we perhaps maybe post some of the outputs generated by these AI models online, and when the AI industry scrapes the internet to gather new training data, some of the synthetic data goes inside of their training data, right? So this is the Lion 5B dataset, and the images that I have highlighted with red are images actually in this dataset that are synthetic data, right? So these come from certain papers some of you might recognize from a few years ago, and this is already happening, right? So, and Lion 5D is not a sort of super recent data set either. So, moral of this slide is that, well, this synthetic data is really maybe the right word would be essentially polluting our data sets, right? So, and I'll say why polluting is the right word in a few minutes. So this creates this self-consuming loop where these AI models are being constantly trained on synthetic data produced by themselves in previous generations. And what I'm going to tell you today is that bad things are going to happen when you do that, right? So this is very analogous to the mad cow disease and how that started. So let's get into that. So my talk is going to have three parts. I'll talk in more detail about what goes wrong when we train self-consumed generative models. They're going to go mad. I'll say what mad is. And then I'm going to propose a regularization term that is made tractable in tandem with hypernetworks to mitigate madness for any generative model that you like. So it's a model agnostic approach. And finally, the tools that we have developed as part of the second part of my talk are really useful in performing few other projects that I'm really excited about, and I'll discuss those in future directions. Okay, so here's the loop. Instead of a snake, I have the actual loop that's happening. So there are three different colors, right? So let's focus on orange for now. It's simplest case, or maybe the obscure case that doesn't really happen in reality. And that involves, well, you have a training data set, right, on the left. You go ahead, as usual, train your generative model on it. This is your real data set, let's say, your ImageNet, for example. And once you do that, you synthesize new samples, right? So this could be with bias or without bias. Here, bias could mean many things. You can think of it as cherry picking. You can think of it as, you know, having a parameter in your generative model that your generative model would sample closer to the modes of the distribution, or rather give you plausible looking images, as opposed to sampling from the tails that might look, you know, a bit, they might have artifacts in them. So you go ahead and sample from it, and this becomes your new training data set. And you do this loop over and over again, right? So I'll be showing results about this soon. We can add more layers of complications, right? We could say, well, in addition to this fixed real data set that we have, what happens if we have new or fresh real data coming in every time that we do this loop, right? So this is more closer to reality, where we have this constant or this fixed real data set, and then we go ahead and scrape the internet again and add to it some new data that perhaps has been posted since last time we made this data set, right? So we're going to also consider this more intricate scenario as well. So this is what I mean by self-consuming loops. And essentially, my claim is going to be that if we train generative models in this self-consumed manner, they're going to suffer from something called model autophagy disorder. Autophagy means just self-eating disorder. And essentially what happens is, unless you have enough, which we haven't quantified how much, unless you have enough influx of fresh, new, real data every time you do this loop, your generative model is going to suffer from loss of variability in the samples. So that means you would see all the samples collapsing, becoming very similar to each other if you're, you know, talking about or working with images, or you'll lose quality, which means the network will start to generate, you know, just garbage basically, right? And depending on the sampling bias parameter that I said, right, you might end in one or the other case. I haven't made these statements super precise. There are more details in the paper, but the variability and quality are quantified in this work by FID and precision and recall, basically. Okay, so what I claim is generative models go mad or become, they lose variability of quality if they're trained in this self-consumed loop, unless you have enough real data provided at every iteration. Okay, and we don't know how much is enough. We have done experiments using toy data set, and we have this phase transition plots, but yeah, that's where we stopped. Let's look at a few examples. So this is the MNIST dataset, super simple, right? And we're training a diffusion model on it, right? Let's not get too bogged down into details, but and we are looking at the 2D projection of this 28 by 28 dimensional images, right? So we use a UMAP projection. So every dot in these 4 panels represent one image. So forget about the right side for now. On the left, lambda equals 1 means that you have trained your diffusion model and you're just sampling from it without essentially changing the sampling bias or without doing something special such that it generates high fidelity images, just sampling. And what I'm showing here on the left is generation 3 means I have done this self-consumed loop 3 times now. So I have trained on real MNIST, created a synthetic data of the same size, trained another diffusion model from scratch on that synthetic data, and have done that 3 times, right? So the red dots show the synthesized data points, and the green ones are real ones. So what we expect really is that the real and synthesized should sort of, the manifolds should coincide, right? There shouldn't be the same thing. We're dealing with the probabilistic phenomena here. We are generating samples from unknown distributions, but as long as the manifolds are on top of each other, we're happy. So what happens when you don't have sampling bias is that you start to see all these MNIST generated images veer away from the true manifold of the data, the green ones, right? So essentially, if I were to plot these red dots, which we have in the paper, they will just look like garbage. They're not MNIST samples anymore. Whereas if I enforce my model, the diffusion model, to create high quality samples by some parameters, let's not get into details, what will happen after 10 iterations is that essentially the model will still create high quality images, and that is here seen by the fact that the red dots are lying on the manifold of real data, the green one, but they have all collapsed, right? So there's less variability in the different digits that we have. So let's look at a more visual example, right? So we all like, images of faces. So this is a GAN model trained on one of the image datasets, FFH. And generation 1 essentially means we have trained on real data, right? Okay, and these are synthetic images. They're not too bad, there's a few odd ones here. Look at this scary person right here, but that's fine. In general, if you're happy, I guess, with the first generation, I'm gonna run this in forward, right? So synthesize, retrain, synthesize, retrain. Generation 1, generation 3, generation 5, So all of a sudden, we're living in a world that everybody is smiling and there's greener backgrounds and everybody is happy. I don't know. I don't want to live here. So I don't have to comment on what are the negative impacts of having generative models that only represent these type of people. Okay. So this is the loss of variability in generative models, right? So let's see if I have more examples here. Okay, so this is not our example. This is obtained from this paper that was a follow-up work to ours, published in Nature. And what they did was they explored examples with the same setting with LLMs, large language models, right? And since training these language models is very expensive, so what they do is they take this base model that I have down here, and then they fine-tune it instead of training from scratch on the synthetic data, right? So you have this prompt here on the original model, which is trained on real data. It says to cook a turkey from Thanksgiving, yeah, you have to prepare it in the oven. You can do this by adding salt and pepper, and goes on by saying that this is a good approach because it prevents heart disease and whatnot, reasonable. And let's look at future durations. Duration 2. All right, it says you have to be able to eat it all at once. Well, I guess that's fair. You don't want to spoil the food. But if you don't have time to do so, you can use other foods like potatoes, beans, and whatnot. All right, it's going off tracks. And finally, iteration 4 is really funny. I'll let you read it. Yeah.
So
Anyway, go ahead.
I'm wondering, in these generations, as you're training on the synthesized data, is the real data as part of the new training data as well?
Well, good question. I think not. I think this is the extreme case, right? So as they say, the training, even the fine-tuning part, they say has taken a few weeks. So if you add more real data into it, so this
Takes longer.
deterioration in quality is going to be slower. So they wanted to get to the point of, quickly showing that something goes wrong. Here we're dealing with loss of quality, right? Clearly, the LLM is not generating something meaningful anymore. All right,
Yeah.
so
Thanks.
yeah, I didn't go into the details of exactly what happens or in what cases we can prove something or all the examples, but feel free to go back and look at the paper. But I really want to talk about today is mitigating this issue, right? So a regularization term made tractable using hypernetworks to stop this issue or to some extent mitigate it, right? So I'm not going to claim that this is going to completely stop it, but it's going to slow it down. Let's see how it works, right? So here it is. So the idea is that can we mitigate this issue or slow down the deterioration of our generative models without having access to fresh real data, right? So that was the bottleneck in our foundings. So people have proposed different approaches as well. For example, some people say, well, we should watermark generated data via generative models so that later on we can sort of separate them.
Ali,
Yes, go ahead.
I have a quick question. So one observation is that if you inject some fresh real data, it prevents the network from diverging, right? But if you have a flow of fresh real data, how helpful is using all the synthetic data?
I'm glad that you asked that, right? So because I get similar questions often. So the idea is that first of all, we are not advocating anybody to train on synthetic data. We are just looking at what might be happening in reality. If you remember my first slide, I showed you a Lion B5B dataset already has synthetic data in it. So you either can remove it or not. But if it's in there, we're going to tell you that, well, something bad is going to happen to your generative model if you don't add new real data in. But back to your point, I don't know really. We never quantified how much real data you need. Some people claim, and this is the part that I said, some people have arguments against our work. Some people, in the large language model community claim that, well, we are using synthetic data and our LLMs are doing much better in different benchmarks. And to that, I respond, well, that's great, but the point that our paper is trying to make is generative modeling accuracy. We're talking about two different things. You can have a model that does well in a benchmark, but it's not approximating the true distribution anymore. So there's nothing wrong with that. But yeah, so here we are dealing with a very precise mathematical problem of approximating distributions. But yeah, the short answer is I don't know how useful it is. We have experiments in the paper showing that if you have a very small amount of real data, synthetic data really does help. This is in the context of Gaussian mixture model, so it's very basic, but there are scenarios that synthetic data helps.
I see. And the synthetic data can come from another model, right? It doesn't necessarily
Of
have to be
course,
from the same.
we did not explore that. So the possibilities were endless. How do we come up with this experiment? But I'm sure somebody has looked into that. I haven't. I don't know it on top of my head, but
okay. Thanks.
yeah, sure. Oh yeah. So I was talking about different ways of mitigating madness. What I set out to do is to do it without introducing fresh real data, which we claimed is the only way you can stop it. Some people want to just, find the synthetic data and remove it and, stop the problem, right? So, but that has its own issues of detecting synthetic data and whatnot, and people are working on it. So that's not there yet. But we're taking this approach, right? So, but let me tell you how we're going to do that, right? So the idea is that can we find or can we regularize training of generative models? And this regularization is going to be model agnostic. It's not going to be depending on a particular architecture. A colleague of mine, whose name was in my second slide, has worked on a different project where he does this medication and in fact benefits from synthetic data in diffusion models, but a very particular approach. But here we are aiming to mitigate madness for the entire genetic modeling frameworks. It's not a model agnostic approach. And the idea is that can we find the fixed point, the self-consuming point loop, meaning the fixed point comes from fixed point iterations in the optimization literature. So the idea is that sort of, can we find this genetic model such that if we sample from it, train on the synthetic data, and train another genetic model on it, we end up with the same set of weights. Sort of, there are many different networks that can maximize the likelihood of your observed data, or can essentially, they're different, but the same even architecture. If you restart your optimization of your generative model, you will end up with different weights, right? So there are different models that can explain your distribution or approximate your distribution. Among all of those, is there one that if we sample from it and train another genetic model on the synthetic data, it gives the same weights back or not? So that is the high-level idea, right? So before diving into the math, let me establish a few notation, right? So this is our typical genetic models. We have a generative model architecture. This could be a diffusion model. This could be a normalizing flow again. Oftentimes you have latent variables going into this network that introduces the randomness, right? So you sample from this Gaussian distribution, you pass it through this network, and every time you do that, you get a new sample x0, x1, x2 from this unknown distribution that you only have samples from, and trying to approximate it, now called p theta. So you might be confused that, well, what is the relationship between p of theta and g of theta? Well, we oftentimes choose the architecture and that automatically imposes a implicit distribution in the output space, right? So don't worry about it. But essentially different architectures or different frameworks for genetic modeling differ in how do you come up with architectures G that allow you to tractably approximate p of theta. Why? Because the training under the underlying core training principle is maximizing the likelihood of observing the data, right? So once you have that architecture, you want to maximize this. So you can explain diffusion models with this, VAs, normalizing flows, GANs with some handholdy arguments. The idea is that sample from this unknown distribution, you normally approximate the expectation with the sum, with the average of the samples that you have. And you try to compute this quantity log p of theta of x, which is the approximate distribution that your generative model is representing, and try to maximize this, the likelihood, right? It makes sense. So this is equivalent to, of course, minimizing the negative log likelihood. And this is essentially what I claim is the underlying training objective function for all genetic models, with some hand-holding here. So what I'm going to do is add a regularization term now that's in the self-consumed loop. We mitigate the errors. All right, so remember this expectation over samples, real samples. This is your real data set that you have samples from, negative log of your approximate distribution. Okay, here it is. This is the meat, right? So let me walk you through it. There are a bunch of changes compared to the previous slide. We'll walk back and forth. First of all, ignore this regularization term. I'll come back to it. There's one thing missing, one thing different. Here I'm using capital X instead of this expectation. Capital X is just the collection of all the samples that we have, right? So essentially, this becomes a sum once you have an IID assumption over these different samples that you have in this big matrix. So the first part is basically the same thing as the previous slide, with one exception, and that is I'm no longer minimizing with respect to theta. I'm minimizing with respect to another network, often called hypernetwork, which is given data as an input is predicting thetas, right? So it's just a change of variables, right? So far. Previously, I had this generative model parameterized by P of theta, and then I would minimize the negative log likelihood over theta, doing the same thing, except that I'm doing a change of variable. Instead of directly minimizing with respect to theta, I have a network that given data predicts theta, and then I minimize with respect to h. It's just a change of variable. So I'll tell you why this is important, but so far, basically, with the expression of this change of variable, we haven't done anything. So it becomes clear now why I need h. So the second term, the regularization term, is essentially trying to find that fixed point. What it says is, well, we have some parameter lambda that we have to tune, as always. Now it says, well, sample synthetic data, so x, capital X bar means a collection of samples from P of theta, not the original P, right? So this is synthetic data. So take your generative model at this current iteration that you have with the current guess of theta, generate synthetic data from it, plug those synthetic samples into this network H. That is going to predict a new set of weights. And these set of weights are hopefully going to be the set of weights of a secondary generative model that represents or approximates the synthetic data. And make sure this second set of weights is close to the original weights that you started from. Okay? So all I'm doing is turning the problem on its head. I said, well, self-consuming is causing my distribution to walk randomly away from the true distribution. Can I stop that? Well, I say at every iteration of your training of your generative model, take your generative model, create synthetic data, train another generative model on it. This is training a generative model. The hypernetwork is given training samples, predicts the weights of a generative model. Without the hypernetwork, you wouldn't be able to really, in an inner loop, train a new generative model every iteration. You would have to, use all the GPUs in the world to be able to do that in a reasonable time. And once you have this new generative model, just make sure the weights that you get with the synthetic data is close to the weights that you get with real data. And that's it. Any questions about what does this equation do and why we can hope to gain some benefits from it?
So here you're trying to get to a network as if it was already trained on a real data, right?
Yes.
So does it discourage that network to learn something additional from the synthetic data?
Yeah, so so this is a glorified data augmentation in a way, but essentially it says among all possible networks that given real data produce weights, given all possible networks that have weight theta that maximize your likelihood, give me the one that if I synthesize samples from it and retrain a generative model on it, I get the same weights back or close weights back. So the premise here is that there are many different generative models that can approximate your distribution, right? Can we regularize and pick the one that if we do the self-consumed loop one step further, we essentially enforce the fact that we don't veer away from the original distribution or not. So it's just a very, so that's basically it. So we weren't sure this is going to work at all. Because as you know, a lot of these generative models are very intricate, the architecture, but it turns out it does work. I'll show you the result, and it works right out of the box. But you can't just use any hypernetwork. You can't just use any network H. There are a few things that you need to be careful about, and I'll tell you what those are. All right, so your hypernetwork should be able to remember the hypernetwork goal here is it mimics the role of training a generative model, right? It takes in data, either real or synthetic and produces weights of a generative model that maximizes the likelihood of the data. So you should be able to apply this hypernetwork to a arbitrary ordering of your data, meaning that if I change the order of images of people's face in the data set, the network weights, the generative model weights shouldn't change, right? Because it doesn't matter what order the training samples come in. So it should be sort of permutation invariant. Another thing is you should be able to train this generative model or apply this hypernetwork to varying number of input data, because I might want to train my generative model in a batch, via batch stochastic optimization, right? So not to input all my training data all at once. And we want to minimize computational overhead. Okay, so I haven't made a comment on that yet, but let me make that right now before I forget in the future. The vol clock time, the time it takes to really train these networks with this change of variable is more or less the same. It's nowhere close to even 1.5 times more. It's basically the same. And I have reasons why that is the case, which I'll show you in the future work section. This is the architecture that essentially possesses this characteristics. It's obtained from this work in the scientific community, scientific computing community, which I work in, and it comes from this paper, this architecture. And essentially, this is permutation invariant. All you do is input your data matrix, which contains different samples. You have an inner network that processes individual samples individually, and then you do an average. So immediately, this average doesn't change if I change the orders, because sum doesn't change. And you can evaluate this hypernetwork over a varying number of samples here denoted by n, because you can, it's not going to break. And finally, you have this outer network that takes this middle representation and maps it to the weights in different layers of your target generative model, right? So the H2 produces weights for your generative model for different layers of it, starting from this internal representation. So both the sum and H2 are highly parallelizable, and that's why this architecture possesses these features. All right, so we went ahead and used this and applied it to a few distributions. So this is a toy distribution, a bunch of 1D distributions, right? A uniform, a Laplacian, different ones. And this is in the context of self-consuming generative models, right? So the horizontal axis shows the generation number, meaning how many times I have done this loop. And the vertical axis is showing the value of the parameter. So these distributions have only, or we are estimating one of their parameters only, which is shown in a blue, the solid blue. The ground truth value, for example, in top left is 1, the uniform distribution. Does anybody know why, if you use maximum, what is the maximum likelihood estimation for estimating the parameter of a uniform distribution? You have a set of samples from an unknown uniform distribution that goes from 0 to some number. We want to estimate that number. What is the maximum likelihood tell you to do? I'll wait 7 seconds. All right, if you write down the math, the maximum likelihood is the maximum value of the samples that you have. So you run RAND in your favorite programming language 1,000 times. It gives you numbers between 0 and 1, 1,000 numbers. And if you try to estimate the parameter 1, which you assume you don't know, the maximum likelihood estimate is the largest value that you have. Anyway, so the red here shows the maximum likelihood estimate parameter as you do the generations, and that's why it's steadily decreasing, because every time you end up with a parameter with a distribution that has a smaller maximum value, right? Because it's very unlikely to sample the maximum point when you're doing uniform sampling. Anyway, so in all of these cases, the MLE, or the maximum likelihood estimation, moves away from the ground truth, the blue line, whereas our approach, sort of stays there, right? In some cases better, and in some cases worse. And by our approach, I mean essentially, instead of doing maximum likelihood estimation, which is this equation, you would do this change of variable with the hypernetwork and add this penalty term and somehow find the parameter lambda of it cross-validation. All right, more interesting stuff. So this is the same again experiments that we showed in the self-consuming generative models go mad paper. So the red curve is essentially the images of people that we saw that went berserk in few iterations. And PLE is this particular approach that I just talked to you about. And on the horizontal axis, again, we see generation. And on the vertical axis, we see FID, which is a metric for how good or how close your approximated distribution is to the original. So lower is better. And what we see is, of course, we're not stopping the madness altogether, but it's significantly slowing it down as compared to if you were to do nothing. And one thing to note is that at iteration 1, which is when you train on real data, you're essentially getting the same performance. It's not like you're losing any quality when you're training on only real data. All right, so this was basically the results. We noticed something also quite surprising when we were playing around with imbalanced datasets, right? So we had a hunch from the original paper, from the previous paper, that when you have imbalanced datasets, the self-consumed loop, essentially, you can see it much faster because that sort of minority class dataset completely vanishes much quicker, as opposed to when you have very nice balanced clusters in your data. So this is a synthetic example that we performed. So we took two digits, I think 3 and 6 from MNIST dataset. So each have, I don't know, how many, 5,000 samples originally in the dataset, right? So 50,000 samples in total. So what we did is we intentionally removed a portion of one of the two digits. I think we removed the 6 digits. For example, up here, the ratio between the majority class to the minority class in the first row of results here is 2 to 1. So we have 2 times more 6s than 3s. Then 5 to 1, 10 to 1, 20 to 1, right? So, and we went ahead and trained a variational autoencoder on these data sets. And what I'm showing here in numbers is, again, the quality in generative modeling, right? So FID oftentimes measures quality as opposed to, the diversity. I'm not going to get into that, but the lower is better, if you remember from the previous plot. So what we noticed was that the minority class, when we used our approach, usually is much, much better represented when compared to when you don't use our approach. And this is not, mind you, this is not a self-consuming loop. This is just you have this data set and you're training a generative model on it. And when you have severe imbalances, your generative model severely misrepresents the minority class because, it's maximum likelihood. It's greedy. It tries to maximize the likelihood, and when it sees, 20 times more samples from one class than the other, it focuses on that, and essentially it gets better representation, of course, on the majority class, but it does much worse on minority. So if you're in a scenario that you're convinced that you want to create synthetic data using the limited data that you have for whatever downstream tasks that you have, and you have minority classes, for example, if you're in medical imaging and you have very few images of tumors, of MRI images, and you want to create synthetic data, be wary that if you do it naively, the quality of your minority class is going to be subpar. So that was a surprising find. Okay, that's all that I had for the results. The second paper is still under review, so they're still working on it. And a few interesting future directions arise after doing the second project. So one is, well, people like to train sort of dynamical systems, right? So for example, weather prediction models are very computationally expensive to run, right? The AI models doing weather prediction are, very easy to run or very cheap to run once you train them. But the issue is that they can't really extend or extrapolate in time more than 30 days, let's say, most of them. And the reason is that the errors start to accumulate, right? So once you use your AI model and give the history of the weather to it, and you predict the next day, and you want to go and predict the day following that, your network is making errors over and over again, and these errors are getting magnified, right? So this happens in different scenarios. It's not just weather prediction. It happens mostly in cases where you have a next token prediction model, and you expect your model to make some errors, and oftentimes the errors magnify. So in case of language models, it's quite different because we're learning distribution over discrete variables. There are only so many words in English, right? So discrete versus continuous makes it a bit sort of the language model less susceptible to this issue. But what you can do with this same regularization term that I described is try to sort of stabilize this learned dynamical models, right? So imagine you have this learned dynamical model that can predict 30 days into the future. What I'm going to do is add a regularization term, the identical one, that it's going to, at every iteration, it's going to extrapolate into the future, let's say 30 days. Now we have a series of data points into the future. And now what I'm going to say is if my stochastic time series is ergodic, meaning that the distribution in time doesn't change, if I train another dynamical model on this future trajectories, the weights should be the same, right? Or I could enforce them to be the same. So the same exact phenomena, instead of a generative model, now you have this sort of dynamical model that sits there. So we have rudimentary examples with basic distributions and basic architectures like RNNs with sinusoids that really shows its benefit in this context as well. So another thing that this veers away a bit from sort of generative models, but we wanted to understand, as I said, why is it that when we add this complicated hypernetwork in the generative modeling domain, why is it that the walk-clock time is not changing that much? Why is it that we are increasing the number of unknowns because the hypernetwork is much more overparameterized than the original generative model? But the training is seemingly happening in the same amount of time, right? So that led us to think about a bit about the effect of hypernetworks on the loss landscapes, right? So, and the question is, can we design hypernetworks that sort of convexify the loss landscape of training deep networks, not only generative model, but any network training? And this is really inspired by this well-known phenomenon in PD constraint optimization, where you have sort of observations from your PDE, and your goal is to estimate a coefficient of this PDE. And oftentimes what happens is that when you expand the search space or relax the problem, things become more convex, the objective function, right? So, and for those of you aware of it, this whole notion of sharp minima and flat minima in deep learning, if you have a convex loss landscape, which is nice and convex and flat, you get better generalization as well. Because at the end of the day, a perturbation to this loss landscape introduced by generalization errors and whatnot, which would affect the location of the minimizer less than if your landscape was very sharp. So let me show you a preliminary result of this, right? So what we did was we wanted to extend the search space when we have convolution layers in our networks, right? So any network that has convolutions in it, you can do this to it. And we have code on it. We haven't wrote the paper yet, but the code is already out there. So the idea is that we know how convolutions work, right? So you have this kernel and you slide it over your image, do dot products, and you get your output image. Well, can we use non-stationary kernels as an auxiliary variable while having our original kernel, and somehow design an optimization scheme such that at the end we obtain the same convolution kernel we wanted to, but in this extended search space, right? So just to give you an idea, on the left is your typical convolution operator. It's a linear operator, right? You can represent it with a matrix vector product. This is how the convolution looks, right? So you have this 3x3 kernel, and it's being applied to the different positions of your image. The non-stationary convolution looks like the one on the right. So every pixel location gets its own set of filters. Without going into the details of how do I solve this extended optimization and how do I get the same 3x3 kernel back, but I'm going to run an example on a 5-layer CNN on some very basic regression task that I generate input data, I pass it through my network to get some output data, and so in this case we have some ground truth weights to work with, and I'm going to do this extension versus non-extension and plot the loss landscape in 2D, right? So there are ways of doing that, and this is how it goes, right? So we are looking at the same space on the left. So this is the space of the loss function, where in higher dimensions is all the possible weights of your network, and each set of weights gives you a value at loss, but they're showing it in 2D, and the colors show the loss value. 0 and 0 means, when you're sitting at the minimizer in both cases. And we clearly see here with this extension, which I didn't describe the details, the loss landscape is super convex. And wherever you start, it doesn't matter. I'm going to start at the 4 corners here and here as well. And I'm going to run the optimization. And you can obviously expect when you have this loss landscape to converge much faster, even because you can take larger steps if you use second order optimization. You're doing first order here. And this is how the loss function works, right? So if I start from the 4 corners, and if I do the extended convolution or the regular, all the extended ones converge with the same speed because essentially it's a ball, right? It doesn't matter. Whereas in some cases, the optimization gets stagnated for the one that the loss landscape was super non-convex. So we are still working on it. So we want to really understand the hypernetwork architecture that we use in the work that I just presented and how that affects the loss landscape. This was just a handcrafted hypernetwork for convolutions. But this itself could, have benefits in generalization of networks, right? So with that, I'll finish. Our contributions was we introduced a model-agnostic madness medication approach, which turned out to enhance the minority class representation at will. We were not expecting that. And for those of you more bogged down with details of implementations, if you want to implement hypernetworks in PyTorch, it's a pain. The hypernetwork output is a torch tensor, whereas the weights that you want to predict are torch parameters, which have a dot tensor attribute and a dot weights attribute. You break the AD if you just plug in the output of a network to the data attribute. It's a mess, but we have released a hypernetwork architecture that you can, a few lines, not only create an automatic architecture for yourself, so you have your downstream network. Of course, you don't want to optimize with respect to it directly. You put requires graph false. And our hypernetwork, you just provide the input dimensions of your data, a few hyperparameters, and your downstream network to it, and it automatically gives you a hypernetwork architecture, as I showed you in my slide. And all you have to do is, define your optimizer over the hypernetwork, and then you're done, right? You pass your input to the hypernet, you get a weight dictionary out, which you can essentially plug that into this abstract functional call in Torch. And what it does is it inputs X, your input, to your downstream network, the network that you care about, using the predicted weights, right? So essentially 2 or 3 lines of changes in your code, and you can now train your code with a hypernet. Right, I'm done.
Very nice, Dr. Siahkoohi.
Thanks.
It's been a great talk. So from the audience, do you have any questions? So I do have one. So you were saying that how the minority class representation from the perspective of a generative model can be improved. I'm wondering if you have done any explicit study on the mode collapse issue that generative models typically suffer from.
So I'll make a comment about that. So we looked into that in our original self-consuming generative model goals map paper, and essentially is whenever you're in the regime of loss of diversity or variability, you're essentially collapsing, right? So in this example that I showed, the mode collapse is not happening. We are still getting different modes, but I imagine if you have imbalanced data sets, you definitely will run into that issue. That's as far as I can share at this point.
Oh, I see. So for this graph on the left, yeah, yeah, it seems that you're still capturing the modes, but
Yeah, on the left, essentially you're veering away from the real
the
data
actual
mining,
modes,
right?
yeah.
So, and you could argue that yes, if I run this for 100 iterations, it's going to essentially maybe collapse into a single point in the middle. But we didn't do that. We have an example with hypernetwork, sorry, with normalizing flows using a toy dataset in the paper that I start with some, toy distribution, and I run that for multiple generation, and essentially it lands on one single point. So essentially it collapses to a single point. But I didn't comment on the actual, things that happen in madness, right? So essentially what happens is your mean of your distribution starts to do a random walk while the variance collapses if you run this process long enough, and you might end up you might get one sooner than the other depending on your sampling bias, right? So in this case the mean has completely walked away already, but the collapse is happening later. But right now on the right things are collapsing more, but perhaps after a while you'll start to also your mean will start to walk away as well.
There is a question on the bridge.
Can
Is
you
the
please? Yes.
Is the fixed point kind of analogous roughly to a point that the synthetic data is neither adding to our learning nor contributing to unlearning?
I think so. Yeah. I mean, so essentially what I want to do with the fixed point is that, so this is how I like to think about it, right? So I'll comment on synthetic data in a second. So I think the process of training a generative model, which involves you have a training data set and you're predicting theta, is somehow the inverse of sampling, right? So you have a distribution and you sample from it. The inverse of it would be, well, let's estimate the parameters of the distribution, right? So in this context that we don't have a closed form expression for the distribution, theta plays the role of the summary statistics of your data, right? So you capture the distribution, all of it in this parameter theta, and it allows you to sample from it again. So the way I like to think about it is that I would like from all possible h's to find the one that is the true inverse of the sampling operator. I mean, this is a bit hand wavy, but I think this is essentially trying to do that, right? So if I really am inverting sampling, or H is really inverting sampling. So if I run it in forward again, obtain synthetic data and invert again, I should land at the same points, right? So sort of that's how I like to think about it. The effect of synthetic, yeah, I don't know if you're undoing the effect of synthetic, because as you said, this would be interpreted as a glorified data augmentation, right? Because at the end of the day, the synthetic data is providing gradient information to H, right? So, but it might be that we are trying to pick a network that generates synthetic data, that the effect of that synthetic data on the weights is sort of minimal when it comes to maximizing the likelihood of the original data. So that is the least nonsensical thing that I can say at this point.
Great. I have a question.
Go
So
ahead.
in your formulation, we are always assume that we have no prior knowledge about which one is a synthetic data and which is not, right? But would that help?
Right. Okay, good point. Here I'm assuming that I don't care what's in
If we
X.
have labels about this is real
Okay,
data,
so
this is not real.
okay. Well, as I said, that's a whole different strategy, right? So people are working on essentially detecting synthetic data and trying to remove them so that this problem goes away. So that's a whole different strategy that you can go about. I haven't thought about how we can, if I have extra prior knowledge about synthetic data existing in this matrix X, how I can exploit that. Well, I would imagine the first thing that comes to mind is just throw them away, but I guess
No, but
maybe there's something. Yeah.
So basically, when I think about people are like web crawling and getting lots of data from the web, and now web is getting filled with all this synthetic data, right? So you practically cannot avoid feeding
Yes.
some synthetic data back. But then I think those synthetic data might be generated with a different model, different data set. So it's,
Yeah.
to my understanding, it's kind of like a knowledge distillation effect you are having when you are using those synthetic data, because those are trained on some other data distribution. So that's why probably we are still learning something from the synthetic data.
Yes.
But we don't want to overdo it. And what I was thinking is, if having some idea, if we have some idea, some say like some confidence, saying like, okay, I'm 90% confident that this is real and that's synthetic. If we can do things in a different way, treat them slightly different way, so that the network doesn't start
Yes.
fully relying on the synthetic versus
No,
the real.
I totally agree. Again, I think I remember seeing a paper doing multiple models at the same time, not just one architecture. And if you think about, mode collapses, just think about the loss of variability. So what happens is you have this distribution, and then the first training model that you train on, it's sort of, less wide. It focuses on one small aspect of it. And then, but if you have a different type of architecture, then you might get a different behavior. It might focus on a different region of the distribution space, and overall you might slow down the madness as compared to this very extreme case that I just presented. And exploiting synthetic data in a way, that reminds me of the paper that I mentioned. Sino has worked on it. Let me put his name up here. So this person. So they really, this is in the context of diffusion models. They say, well, if I have synthetic data, what I'm going to do is I'm going to use essentially I'm going to use a score function that is obtained from synthetic data. I'm going to guide my diffusion model to sort of veer away from the gradient or the score obtained via the synthetic data. And by playing around with the contributions of the score of the real versus synthetic, they end up even outperforming in terms of quality of generative modeling as compared to when you only have real data. So if you're interested in exploiting the fact that you have synthetic data, take a look at his book, his recent book.
Okay, yeah, thanks. Sounds
Yeah,
good.
sure.
So do we have any more questions? So if not, thank you, Dr. Siahkoohi. Thanks for the very interesting talk, and it was very informative.
Thank you
Yeah,
so
thanks
much
a lot.
again.
Yeah,
Thank you for the invitation.
Yeah, glad to have you here.
Thanks.
Thanks. Bye, everyone.
All right. Bye-bye.
Thank you. Bye.